Hi everyone. In today's video, we're going to continue our journey through carbonyl chemistry. This time, we're going to look at carboxylic acid derivatives. It's my goal that by the end of this video, you would be able to identify carboxylic acid derivatives, rationalize the relative reactivity of carboxylic acid derivatives, and then propose reasonable mechanisms for nucleophilic acyl substitutions. Okay, so let's get started. So recall that you can take a carboxylic acid and reduce it all the way down to an alcohol. And this can be readily done using lithium aluminum hydride as your hydride reducing agent and then protonating it with some kind of acidic source or some proton source, and you will get your alcohol. We call the carboxylic acid its oxidized form because if you really just think about the carbonyl carbon, you would see that that carbon is bonded 3 times to electronegative atoms. So it has 3 bonds to electronegative atoms in the carboxylic acid form. Meanwhile, in the reduced alcoholic form, that same carbon has only 1 bond to an electronegative atom. The greater amount of bonds carbon has to electronegative atoms, the more oxidized that carbon is. So essentially, you can kind of look at that and see that, oh, this molecule has been reduced. So while we learned this, carboxylic acids can also react to form other molecules which have the same oxidation state. In other words, 3 bonds to electronegative atoms. One example is if you take your carboxylic acid and then treat it with a SOCl2, which is a thionyl chloride, it's going to convert this carboxylic acid to what we call an acid chloride. You've actually seen what an acid chloride is, and this is a very standard way of preparing acid chlorides. Note that the acid chloride also has 3 bonds to electronegative atoms, and so this acid chloride is going to have the same oxidation state as this carboxylic acid. And so because that's the case, we call this acid chloride a carboxylic acid derivative. And then here are other carboxylic acid derivatives that we are going to be seeing over and over in our text. So once again, if you just consider the carbonyl carbon that I'm highlighting over here, all of these carbons have 3 bonds to electronegative atoms around that carbon. So note that the same also goes for your nitrile. That nitrile carbon has 3 bonds to nitrogen, which is a more electronegative than the carbon. So all of these are considered carboxylic acid derivatives. So you have your acid anhydride, I've highlighted over here. It's basically a carboxylate group as a substituent on your carbonyl. You have your ester, which is basically an alkoxy group on the carbonyl, or an amide, which is an amine group on the carbonyl, and then your nitrile, which is basically a cyano group. So it turns out that if you were to rank the relative reactivity of these different carboxylic acid derivatives, your most reactive carboxylic acid derivative is going to be your acid chloride, and it's going to be followed by your acid anhydride, and then it'll be followed by your esters, and also by your amides, and then your nitriles. Importantly, your carboxylic acids and your esters have about the same reactivity, so they kind of all lay around this corner. But that being said, the reactivity decreases as you go from an acid chloride to a nitrile. And so why would that be the case? Well, I think it's important if you were to try to understand this trend to really just look at some case studies. So we're going to look at the reactivity of this acid chloride, and then we're going to look at its reactivity of this amide. And I believe by when you see these two and you're able to explain them, you will be able to also understand the rest. So we're going to ask ourselves first, why are acid chlorides so reactive? And then in order to explain this, we have to take into consideration 2 effects, which we keep on bringing back over and over again. One is our induction, and then the other is going to be resonance. I think we can all agree from an induction point of view that the carbonyl CO bond has a bond dipole moment going towards the oxygen. All carbonyl groups possess this quantity, so there's no need to even look at this particular bond dipole when you're trying to compare the relative reactivity across the different carboxylic acid derivatives. However, for the acid chloride, you also have a carbon-chlorine bond, which is very polarized, and that would also have a very strong bond dipole moving towards the chlorine, which is going to make that carbon significantly electrophilic and very ready for nucleophilic attack. But you might say, well, we could draw a resonance picture, which ends up functionally donating chlorine's electron density towards the carbonyl center and then forming this particular resonance form. But recall that pi bonds between atoms at a different energy levels are going to be fairly weak. So you have a carbon in pair 2, a chlorine in pair 3, and you're trying to overlap their p orbitals in a side-on manner. That's going to be a pretty weak resonance contributor because of the size mismatch of the overlapping p orbitals between those two nuclei. And so really, this resonance form is really not going to play a significant role in the reactivity around the acid chloride. And so your induction becomes a much stronger argument in this particular scenario. Okay, so now that we've established why acid chlorides are very reactive, it's an inductive effect, let's establish why amides are so unreactive compared to acid chlorides. So now we look at the carbon-nitrogen bond, and we realize that because the nitrogen is just one over to the right of a carbon, while yes, there will be a dipole moment going towards the nitrogen, it's certainly not going to be as strong as your carbon-chlorine. And so your carbon-nitrogen would have a fairly weak bond dipole moment towards the nitrogen. And then in addition, the resonance picture would then relate to you that the lone pair in nitrogen can actually donate its electron density into this carbonyl center, which will form this resonance form. But unlike the carbon-chlorine pi bond, which is not a very strong pi bond, a carbon-nitrogen double bond is actually fairly strong. Carbon and nitrogen are on the same period on the periodic table, and so their overlap of their p orbitals would be pretty nice because of a size match between both of them. And so this would be a significant resonance contributor to your amide, which would then also, once again, attenuate the electrophilicity at that carbon, making it less susceptible towards nucleophilic attack. And so between these two, you can kind of see now you can rationalize the reactivity of these different carboxylic acid derivatives by really looking at your inductive and your resonance effect, and then seeing how these different effects affect the reactivity of the carboxylic acid derivative. Okay, so now let's delve a little bit more deeply into the reactivity around carboxylic acid derivatives. And we're going to introduce a new reaction mechanism called the nucleophilic acyl substitution. But before we get too deep into the mechanism, let's start thinking about just why carboxylic acid derivatives will be different from like the aldehydes and the ketones that we've learned earlier. But first, let's establish that because carboxylic acids also have carbonyl groups, just like an aldehyde and ketone, the reactivity at that carbonyl group is fundamentally the same as the reactivity with the aldehydes and ketones. And so in the same way that nucleophiles can come in and attack the carbonyl carbon of your aldehyde or your ketone and then engage in a nucleophilic attack, the exact same thing can happen with any of your carboxylic acid derivatives. And so your nucleophile can attack the carbonyl carbon of any of these carboxylic acid derivatives in a nucleophilic attack step. So all of that is basically the same rules apply essentially across the board. The major difference here is that the carbonyl substituents, or the groups around the carbonyl compounds for carboxylic acid derivatives, can function as leaving groups. So while a hydrogen in an aldehyde or an alkyl group in a ketone will not serve as good leaving groups no matter how you try, your chlorine on an acid chloride actually can be a good leaving group. So is your carboxylate group. So is your alkoxide, as long as you're in the correct conditions and in correct protonation states, as well as in some cases, your amines. So you can actually make these groups good leaving groups, but for your carbon and your hydrogen, they pretty much can never be made good leaving groups. And that is what then differentiates the mechanisms with your aldehydes and ketones versus the mechanisms with your carboxylic acid derivatives. Okay, so now that we've established that, we can say that carboxylic acids derivatives undergo what we call a nucleophilic acyl substitution. So nucleophilic acyl substitution, as the name implies, results in the substitution of a group in your substrate with another group in your product. So you're a carboxylic acid derivative with a L. We're going to call L a leaving group. Now it could be any of those groups that we had just talked about, can be substituted out with a nucleophile in your flask to form a new carbonyl containing compound with that nucleophile attached to the carbonyl carbon. So it might come as no surprise that the first step in your mechanism under basic conditions would be a nucleophilic attack of that strong nucleophile to a carbonyl center and then the CO bond, pi bond break in, which then leads to your anionic tetrahedral intermediates. And this is where things differ between the aldehyde and ketone reactivity with the carboxylic acid reactivity. So note that because you are with a carboxylic acid derivative, now at this stage, both the incoming nucleophile and this L group that is in the tetrahedral center can leave. And if your L is a better leaving group than your nuke, the oxygen lone pair can come down, reform a carbonyl pi bond, and then break off the Cl bond, and then the L group leaves to form your product. So note that this is your loss of a leaving group step. We've seen this before, but now it's actually the group that was on that carbonyl compound originally that becomes the leaving group in this particular step. So by now we're familiar that under basic conditions, your reaction mechanisms are typically much shorter. Under acidic conditions, you still have the same fundamental reaction going on. So it's a nucleophilic attack at some point, and then a loss of a leaving group at some point to then form the nucleophilic acyl substituted product. However, because you're under acidic conditions, there could be several proton transfer steps that can happen in between these two major mechanistic steps. In the most extreme case, under acidic conditions, let's say you have now a protonated and cationic nucleophilic reagent in the flask. Well, your carbonyl oxygen, as we've seen, can get protonated by that acid in the flask, forming your activated carbonyl compound. So now you formed a really hot electrophile, and any nucleophile weak or strong can come in and attack that carbonyl carbon, right? So that'll be your nucleophilic attack step occurring at this point, which then in this case results in a cationic tetrahedral intermediate. And once again, we are under acidic conditions, and so quite a bit of proton transfers could occur. Let's assume that the leaving group needs to be protonated in order for it to leave. And so if that's the case, then you need a proton transfer that will get rid of this proton on the nucleophile, and a proton transfer that will put a proton on this leaving group, which then gets you to this new tetrahedral intermediate with your activated leaving group. But once you get here, now you've created a good enough leaving group under acidic conditions, and then the leaving group will leave, which then results in the reformation of your sp2 trigonal planar carbon. Now you have basically a product, however, it's protonated, and so you need one more proton transfer step to then form your product. Okay, so note that in this case, you fundamentally went through the nucleophilic attack and the loss of a leaving group step, really the same in your basic conditions, but that's now sandwiched between four proton transfer steps, right? So this is definitely the most extreme case where you're under acidic conditions, and this is the most extreme case under basic conditions. But please note that there are several iterations of this particular mechanism. So the reason why I've highlighted our proton transfer steps in green is that they're actually not necessarily fixed. So sometimes you may not actually have all four proton transfer steps. It might be one. And then also the order in which these proton transfer steps occur in the mechanism might be different. So sometimes the nucleophilic attack can happen before the proton transfer step. And then sometimes you might also have this proton transfer happen after the loss of a leaving group. And so what we're going to do for the rest of this video is actually to walk you from conditions where you have very basic reactions with very strong nucleophiles and very reactive electrophiles. And then you're going to go through some intermediary mechanisms that kind of linger in between the basic and acidic form. And then you will get to the very acidic mechanism where you have not so reactive electrophiles and also not so reactive nucleophiles. Okay, so here's an example of a nucleophilic acyl substitution reaction, and we're tasked to think about what the most likely mechanism for this reaction would be, or at the very least, a reasonable mechanism. So in order to approach a problem like this, it's a good idea to establish some key things. First of all, what kind of carbonyl compound do we have? Is it going to be very reactive or susceptible to nucleophilic attack, or not so susceptible to nucleophilic attack? And we've already established that our acid chlorides are very susceptible to nucleophilic attack, which means that carbonyl carbon is very, very reactive. And then we established that we are indeed dealing with a strong nucleophile. So you have a strong nucleophile and a carboxylic acid derivative that is very susceptible to nucleophilic attack. And then lastly, we got to establish what kind of condition are we in, acidic or basic or somewhere in between. Here, it's pretty clear that we're under basic conditions. So it would make sense that our mechanism should really not wait for anything, right? The nucleophiles are already ready for attacking. The electrophiles are already prone to getting attacked. And so your nucleophile is going to attack the electrophile and then engage in a nucleophilic attack step. You're going to form your tetrahedral intermediates. And once again, because you're under basic conditions, one, it really just doesn't matter. The chloride is just a good leaving group. It's going to be susceptible to leaving. And then this O minus is going to be susceptible to falling back down to collapse back into a trigonal planar sp2 carbon center. And so it should come as no surprise that you engage directly in the loss of a leaving group, and then the chloride leaves, and then you form your ester. Okay, so that's your extremely basic conditions. This is the extreme. You just have a nucleophilic attack and a loss of a leaving group. Okay, but now what if you had this reaction? So it's only slightly different. You still have your acid chloride, but now instead of your sodium methoxide, you actually just have ethanol. And now you're producing a small amount of HCl every single time this reaction happens, and then you still form your ester. So we're still going to establish that we have a strong electrophile here. So this acid chloride is going to be very susceptible to nucleophilic attack at that carbonyl carbon. And that's even though you have a weak nucleophile in the flask. The reaction is also done in a somewhat neutral but maybe mildly acidic condition, given that you're producing HCl as the reaction moves forward. And so now you have these three data points that should actually start to inform the way the mechanism is going to occur. Okay, so if we have an acid chloride, remember that we just said acid chloride is very, very susceptible to nucleophilic attack. It actually doesn't matter how weak the nucleophile is because of how reactive this acid chloride is. It's going to react immediately with any nucleophile in the flask, which means that our first step is really still going to be the nucleophilic attack of that weak nucleophile on this incredibly strong electrophile, which, yes, is going to form this zwitterionic species. But once you get to this intermediate, you can see that you are now in just the best possible set of events for this tetrahedral intermediate to collapse. You have now formed that O minus, which is really going to want to get neutralized. And you have a really good leaving group in this particular tetrahedral intermediate. So before any proton transfer can actually occur, you're going to have a very rapid loss of a leaving group, which releases the chloride to the flask and then forms this cationic product. And then it's at this point in which another ethanol molecule can then come in and deprotonate your cationic ester to form your product. So notice here, it's still nucleophilic attack, loss of a leaving group, but because they're dealing with this combination of a weak nucleophile, really strong electrophile here, and then somewhat of a mildly acidic solution, you essentially kind of can get wrapped up into one more proton transfer step at the very end of the reaction. Okay, so now here's another one. Now this time we're taking an ester, reacting that with an amine under acidic conditions, and we're going to get our amide from here. Once again, this is a nucleophilic acyl substitution, as we're substituting out the alkoxy fragment with the amino fragment in this particular molecule. And so we say that because we know that the ester is going to be less reacting at the acid chloride or the acid anhydride, this is not actually a very susceptible molecule to nucleophilic attack, so not so reactive. That being said, though, our amines are strong nucleophiles. So we've established that way back when, but our amines are really strong nucleophiles. And we are under acidic conditions. So all of this is going to really affect the way our mechanism is going to look. So let's try to propose a reasonable mechanism for this particular reaction. Okay, so in our proposed mechanism, so we start with our ester and we say, okay, it's not so reactive, so maybe we might need to activate that ester. But you have to hold on right there and look at your reagent and realize, oh, no, no, no. We have a really strong nucleophile in this flask. It really doesn't matter how strong this ester is, that amine is going to attack that carbonyl carbon. And so very similar to what we've seen with the reaction of an amine to a ketone or an aldehyde, the first step, even though it are acidic conditions for this reaction, is your nucleophilic attack on that carbonyl center, and then you form a zwitterionic tetrahedral center. Okay, so this is our next intermediate. But now we're in a bind. We don't have a good enough leaving group on our alkoxy group here, especially under acidic conditions. So as opposed to the chlorine that we've seen in the past, this is not a good leaving group. And we are now under a pretty nicely acidic condition, which means that this O minus is really not going to linger so long. So because the alkoxy group is not going to leave just yet or just so easily, the most likely next step here is going to be a neutralization of this anionic oxygen, which we may then establish in our proton transfer step. Okay, but in doing so, now we've made this oxygen somewhat comfortable on that tetrahedral intermediate, which is fine for the stability of the molecule, but not so great for our ability to disrupt this CO bond. And this oxygen is still not a good leaving group. And we now have a cationic nitrogen that we need to worry about. So our sequence of events that might make sense in the formation of this amide is to get rid of this positive charge of the nitrogen by deprotonating, and then protonate the oxygen in this particular leaving group, which would then make this a much better leaving group under acidic conditions, which then gets us to this particular tetrahedral intermediate, which now we can see, okay, under acidic conditions, this group is now going to be fairly susceptible to leaving. And so we can then imagine a loss of a leaving group step here, which looks like this, frees up your methanol in this case, and then takes you to this protonated or cationic product. And then from here, it's just one more proton transfer step to get you to your amide. Okay, so once again, remember or note here that fundamentally it's still a nucleophilic attack and a loss of a leaving group, but now you have the 4 proton transfer steps. Okay, So we're going to do one more of these and then we'll be done. Okay, so now consider this particular nucleophilic acyl substitution reaction. So here we have a carboxylic acid, we have ethanol in their acidic conditions, and we get this ester. So as we've established, the carboxylic acid has relatively similar reactivity to the ester. And so just like the ester, it's really not that electrophilic. It's not so susceptible to nucleophilic attack at that carbonyl carbon. In addition, the nucleophile, which is ethanol, I mean, that's really not that strong either. So you're dealing with a weak nucleophile, and so that's why this acidic conditions were added. Okay, so you're seeing this reaction for the first time and you're trying to figure out, all right, so what's the possible substitution mechanism here? So in this case, with a weak nucleophile and a kind of weak sauce electrophile, you're not really going to have a nucleophilic attack in that first step, right? There's nothing really necessarily making that first step be a nucleophilic attack, but you're under acidic conditions. So you can imagine the carbonyl oxygen, just like your aldehyde and ketone, can get protonated, which then gets you to this activated carboxylic acid. Okay, so now we're in business because now we have a really hot electrophile. So even though our nucleophile is fairly weak, because we formed this, anything is going to attack that carbonyl carbon. And so the next logical step here will be your nucleophilic attack step, where your ethanol attacks the carbonyl carbon, and then you form your cationic tetrahedral intermediates. So note here that what we're trying to do is make the hydroxyl group a good leaving group, and then this should also not be a good leaving group. So you want to do a proton transfer that will get rid of the proton on the blue oxygen and then put it on the yellow oxygen. Note that both of these OH groups are just as equally likely to get protonated and you will get the same product. But let's just kind of be for consistency's sake, we're going to worry about just the group that is highlighted in yellow. And now that it's water under acidic conditions, that's going to be a pretty good leaving group. And so we end up with this cationic ester, or this protonated ester, which is basically almost to your product, okay? And then now what we just need to do is deprotonate that ester, and then we form your product for real, for real. So I would like to highlight again that the reaction is fundamentally a nucleophilic attack and a loss of a leaving group. Your decision making is really where and how many proton transfer steps do we need to do in order to get to our product, and it would still be consistent with the flask that we have at hand. Okay, so we've identified carboxylic acid derivatives. We've been able to figure out like the relative reactivity of these derivatives, knowing that our acid chloride is the most reactive and then our nitriles and amides are just not so reactive. And then we've used that understanding of our carboxylic acid derivatives, as well as our understanding of nucleophilic addition reactions with aldehydes and ketones. And we've run through a series of reaction mechanisms that are essentially nucleophilic acyl substitutions. So the goal here for you is to sort of delve right in, find new reactions, and just propose mechanisms for those based off of what is in your flask. And you need to ask yourself every step of the way in your mechanism, does this make sense? Is this step consistent with the conditions I have and the reagents in our diamide flask? Thank you so much for watching this video, and I will see you in class.